All right. Other questions about the acetal formation mechanism? Okay. Let's run through acetal hydrolysis. This is just going to be the microscopic reverse of the formation mechanism. So this should be review. Frankly, I could send you all home and make you do this on your own, but I kind of feel like walking you through it once. So starting with the acetal, again, if you're worried about what to do first, simply consult the formation mechanism, start at the end, and do the reverse. So just as the last step was deprotonation of one of the OR groups, so the first step of acetal hydrolysis should be protonation of one of the OR groups to turn it into a good leaving group. That's going to lead us one step backwards to exactly the same intermediate as we saw previously. Now, if we want to know what to do, we can again consult the acetal formation mechanism. The previous step was attack of an alcohol on an oxonium ion to give us this intermediate. Therefore, the microscopic reverse of that should be kicking off of that alcohol as a leaving group to give us that same oxonium ion, and then, of course, the alcohol as a leaving group. If we want to know what to do then, we consult the formation mechanism, noticing that in the previous step, we had this intermediate and water got kicked off. So the microscopic reverse of that is water attacks the carbonyl carbon and breaks the pi bond, and this gives us that same intermediate with a positive formal charge on what used to be water. If we want to know what to do then, we consult the previous formation mechanism. The intermediate previous to that was the neutral hemiacetal. We can form that by simply removing a proton from the positively charged oxygen, and that's going to give us our neutral hemiacetal. And once you get there, you know you're halfway through. To figure out what to do next, we consult the previous formation mechanism. We need to get this to this intermediate where it's the alcohol OR group that's protonated. So we'll simply use the acid that was present and regenerated in the previous step to protonate that OR group. At this point, you should sort of start to be able to see the finish line. With the protonated OR group, we have converted that OR group into a good leaving group relative to a neutral OH kicker-offer. And so we will kick off that. I don't like where that plus charge is, so I'm going to move it, sorry. We can kick off the protonated OR group as a leaving group. That gets rid of our second equivalent of alcohol. That takes us to this oxonium ion, and then all that's left is to regenerate our acid catalyst and our aldehyde, in this case product, because the reaction is acetal hydrolysis. Normally, if you wanted the hydrolysis reaction to occur, you would do this reaction with aqueous acid, because a key step is adding water as a nucleophile to the oxonium ion. So to summarize, if you want the forward reaction to occur, you start with the aldehyde, you start with your alcohol, and you need an organic acid. And you need this to be run without any water, and in fact you're going to need to remove water. If you do that experimentally, you'll get the acetal. On the other hand, if you start with the acetal and then you want to hydrolyze it, you can use any aqueous acid with an excess of water, and that's going to get you to free the alcohol and go back to the aldehyde. Okay? All right, anything we need to say more about that? Yes, please.
Does it work on
Works on ketones exactly the same, only what's H attached to the carbonyl carbon would be another R group. Yeah?
Why does it need to be organic?
Why does it need to be organic? I just mean not aqueous. So some acid, I've given you some options, toluene sulfonic acid, TSOH, or acetic acid, just not like aqueous HCl. Because if you add water, that's going to take you back to the starting materials. Others? Yeah?
This doesn't work on esters, right?
Doesn't work on esters, yeah. We're going to learn what to do with esters in chapter 16, but esters generally, you can hydrolyze esters, so stay tuned. We are going to do this reaction on esters, and it is going to have an effect, but we're not going to make acetals with esters as starting materials. There is such a thing, it's kind of weird, and it's not covered in your text, so we're going to ignore it. All right, others? So this is an example. We talked about protecting group strategies earlier, and it's a group that gets rid of a problematic functional group, but it's easy to install and easy to remove. The acetal is actually a really great leaving group used in a lot of cases. I'm sorry, a really great protecting group used in a lot of organic reactions. And I want to just give you an example of a couple of them. So I think this example is straight out of your text. And maybe this is where the question about the ester comes from. If I had this ketone plus ester molecule, and suppose I wanted to do a reaction with the ester, but I wanted to leave the ketone intact, or at least do something different to the ester than I want to do to the ketone. If I used just an organolithium reagent followed by aqueous workup, what would be problematic is I would expect the ketone to react via an addition reaction, and then I would expect the ester to react via nucleophilic acyl substitution first to give us the ketone, and then another equivalent to give us the tertiary alcohol. That's a review of chapter 13. But I've got what I would call a selectivity problem. What if I wanted to just react with the ester instead of the ketone? And so one strategy to sidestep that, and I guess I'll put in parentheses, it's helpful to know for this example maybe what my desired product is. Suppose I want to get out this, but I don't want the organolithium reagent to react with the ketone. I'm going to sidestep that with a protecting group strategy. So I want to make an acetal out of the ketone. Now I can do this because ketones are more reactive than esters. So if I'm careful, I can add an organic acid, and again, let's just say for our purposes this is acetic acid, maybe let's say TSOH. I know that one scares you, that's why I'm exposing you to it so you can get over your fears now. Go look it up, it's from 351 and it's just an organic soluble acid. And then for an alcohol, I could choose basically any alcohol I want, though it should be cheap and the reaction should be high yielding. One interesting choice is this diol. And the reason we choose that diol, I'll illustrate this in a little bit, is it comes with both alcohols in the same molecule, and it makes making the acetal really efficient. So if we do that first, that will make the acetal out of the ketone and not the ester. So at this stage, I know I've drawn something that looks like a little guy, maybe a bird of some sort. I don't know, there's like two eyeballs. How did that happen? Let me draw for you an intermediate oxonium ion that would have been made if you draw the mechanism. This is after we protonate the ketone, then one of the alcohol oxygens attacks, we do some proton transfer, and water leaves as a leaving group. The intermediate that would be formed would look like this. This is exactly analogous to, if we scroll out for a moment, this oxonium ion where now we're ready for a second equivalent of alcohol to come back in and attack. The only difference is now the second equivalent of alcohol is right there in the same molecule, and in organic chemistry, and all chemistry actually, intramolecular reactions are fast. So it's actually really fast to attack the carbonyl carbon. And if you follow that through, this acetal is the product. I know that when you're not used to seeing something like that, your brain sees this, your brain sees the little guy and says, I don't know what to do with that, and then you forget everything you ever learned about acetals. Don't do that. If you can't stand the fact that those two R groups are connected to each other, simply do this. Surprising how much better that makes it, right? Suddenly you know what you're doing. Okay, one of the skills you need to get in OChem is the ability to simplify more complicated structures into things that you recognize. So again, to sort of increase your ability to tolerate this kind of thing, I'm going to leave it drawn there. But you are totally welcome to abbreviate and draw it as the much friendlier that. Okay? All right, fine. I will also pause to point out that there's a whole area of, well, there's a group at Rice University in Houston that attempted to get people interested about 20 years ago in chemistry by making what they called anthropomorphic molecules involving acetals, because when you draw them, they look like heads. So I kid you not, go look this up. We're not going to do this. It's not worth our time in class, but it is kind of fun. Go Google nanoputations, so named for the Lilliputians of Gulliver's Travels, and they're molecules that look like people if you squint and try not to ask too many questions. All right, with the acetal installed, one of the neat properties of acetals is that they are stable to basic conditions. There's no acidic protons, and because the carbon-oxygen sigma bonds are strong, they are resistant to nucleophilic attack. The thing that made the ketone problematic to begin with was this low energy pi star that a nucleophile could attack. Acetals don't have a pi star. There's no pi bond there. So now that we've installed the acetal, we can proceed with a reaction involving step A, the organolithium reagent, and step B, aqueous workup. And as long as that aqueous workup is neutral and not acidic, that should allow us to convert the ester into the tertiary alcohol without doing anything to the acetal. And then, how do we remove the acetal group to get our desired product? Yeah, that's just acid and water. That hydrolyzes the acetal. Again, if you want to really push yourself, you could be like, okay, I want to draw the mechanism for hydrolysis of that acetal to make sure I can withstand the alluring eyes of the head-like creature on this molecule. I don't know. Go ahead and try to do it. You should totally be able to do it, but if you can't, it's fine. Just abbreviate those alcohols as OR groups, and it should be a lot more straightforward. Okay, so that's an example of an acetal as a protecting group for a ketone. There are other cases, not from your text, but maybe I'll just give you a brief example. There are some cases in organic chemistry where we need to tell the difference between various alcohols. Oh, shoot, do I dare do this? Probably not. So I'm going to abbreviate some things here. P here stands for some protecting group. R there stands for an alcohol. It is pretty easy in organic chemistry to tell a primary alcohol from these other secondary alcohols. And the way you can distinguish between those two is sterics. So it's pretty easy to take, say, the starting material that I've drawn here, which is glucose. It's pretty easy to modify that primary hydroxyl group with some kind of protecting group, which I'm just abbreviating as P, and you don't need to worry about what that is. It's also pretty easy to take care of this OH group because, as you notice, in glucose, what I've drawn here is an acetal. The glucose structure itself, as we learn about carbohydrates, comes as a hemiacetal. It is really easy to convert a hemiacetal into an acetal. So we can also modify that OH group. But then what about the three other protecting groups? How can you tell one from the other? And it actually is pretty easy. I wouldn't expect you to predict that this would happen. This is not a fair predict products question. I'm just showing you something organic chemists do. You can actually take a ketone or an aldehyde. In this case, let's see. I think the ketone or the aldehyde of choice is this benzaldehyde, and use some, again, organic acid, maybe toluene sulfonic acid. And you can selectively modify two of the secondary alcohols without touching the third. And the reason for this has to do, to some extent, with sterics. I kind of screwed up, but whatever. I don't like that, but it's okay. Don't anybody write that down. But basically, you can, because I'm pulling this out of my head and I'm trying to remember what's actually done. But basically, you can use, do you see what the approach here was not to protect a ketone, it was to protect some alcohols. So in this case, the alcohols above, we were trying to protect the ketone and using the alcohols as the protecting group. Now we're trying to protect the alcohols using the ketone as the protecting group. But there is your acetal. As I said, that's not, I wouldn't expect you to do this in a predict the products question. It's not a fair question that way, but it's designed to illustrate that you can use acetals both as protecting groups for ketones and alcohols. Okay, so with that, I'm going to erase all the evidence that I ever talked about that from the video. It'll still, I'll just leave it there. What have I got to hide? As I said, I don't know. When I write down things like this, someone always comes to my office and says, do I actually need to know that? And my response is yes, everything I say is of equal importance. But so I'm going to add a disclaimer here. Don't worry about the specifics here. The thing to understand is that you can use acetals to protect alcohols. And that's what I want you to get out of it. And I'm signing here in blood. And there's little drip marks so you can tell. All right, you can hold me to that. All right, that's acetals. Anything more you want to say about that? Yes?
I know we talked about cyclic hemiacetals.
Yeah.
But do we need to deal with like big products like, oh, it's going to stop with the semi-acetal?
Okay. Good. Your text points out, and I've said that hemiacetals, thank you for pointing that out. I'd sort of forgotten that. Hemiacetals are not very stable, and they are intermediates. You either go backwards to the carbonyl starting material or forwards to the acetal. The exception to that is that cyclic hemiacetals are often stable. So as an example, I'm going to draw the structure of an alcohol. This is actually an alcohol that has an aldehyde in it. I'm drawing it in this pseudo-chair orientation for a reason. This is D-glucose. And as I said, you don't need very much acid to catalyze formation of acetals and hemiacetals. So it turns out that even at physiological pH or pH 7, there is enough acid to catalyze the interconversion of glucose into a hemiacetal. And this is the stuff of nightmares if you don't know how it ends up, because as you look at that molecule, glucose is both an aldehyde, so I'm going to highlight the carbonyl carbon as we've done previously. Here is the carbon on one side, the proton on the other. Here is the carbonyl oxygen, all the important ingredients for the hemiacetal. And the alcohol is in the same molecule. So what we're going to be doing here is called intramolecular, that means in the same molecule, hemiacetal formation. And when you do this, you make a cyclic acetal. The question is, of all the alcohols, which is the right one? I know you detest uncertainty. And I'm here to tell you that it is going to be a feature of the rest of your life. So you got to get used to it. But fortunately, there's some guiding principles here for the cyclic hemiacetals. And the idea is you're going to form the most stable ring. Now, we know some things about rings from 351, right? That ring strain makes 3- and 4-membered rings somewhat less stable than 5- and 6-membered rings. And that 6-membered rings are great because you can adopt a chair structure where there isn't any angle strain, and there's also not a lot of torsional strain. So if you can form a 6-membered ring for a hemiacetal, that's probably the more stable one. So all we're going to do is start counting from OH groups to the hemiacetal carbon, or to the carbonyl carbon, to see what size ring we could form. Start with this one. Oxygen is 1, 2, 3. 3-membered ring. I mean, if you want to force me to, but let's see if we got better choices. This one. 1, 2, 3, 4. Better, but not great. 1, 2, 3, 4, 5. Okay, 5 might be okay. I'm going to write a number 5 by this OH group just to have in my mind the size of the ring. What about this one? 1, 2, 3, 4, 5, 6. Bingo, that's the magic number for ring size, because again, as you learned about chair conformations, a 6-membered ring can minimize angle strain and torsional strain. What about this other one? This would be a 1, 2, 3, 4, 5, 6, 7-membered ring. If 6 is great, is 7 better? And the answer is no, 6 is the sweet spot. There's a lot of reasons behind this. You could learn more in a grad level organic chemistry class, or you could actually try to build some models and test it for yourself. But in general, when you have the choice, you're going to form the most stable hemiacetal ring. Okay? Yes?
7 and 5, is there a difference?
7 and 5, there is a difference, not one that I expect you to predict. Yeah. Okay, yes?
Just to understand correctly, basically the carbonyl carbon is going to become an OH group, and it's going to be bonded to the alcohol that's going to become the O that's kind of close to the ring.
Yes, the carbonyl carbon, the blue and the orange atoms are going to be bonded together to close the ring, and the pink atom is going to be an OH group. Yep, good. So you can see now why I drew it this way, because I knew which way this was going to go. I'll highlight the new bond that we form in orange. You can draw the mechanism for this if you want to, but this is the alcohol that does the attacking of the oxonium ion. The other OHs are less reactive because they lead to less stable products. Now it turns out for glucose, you could imagine, depending on the conformation of the molecule, that OH group in our hemiacetal product might be oriented in one of two directions. In other words, imagine if I rotated around this carbon-carbon bond between the carbonyl carbon and the alpha carbon, I might have had a conformation in which the proton is here and the OH group is down there. I'm not going to draw that, but can you imagine that? And if that OH group, if that carbonyl oxygen had been pointed downward, I might have gotten this stereoisomer as product. I'm drawing it kind of quickly. Sorry about that. Again, here is the new bond that we made. Here's what used to be the alcohol. Here's the carbonyl carbon, the, oops, there we are, proton, and the R group, and then the OH group. In one of these hemiacetals, they're both hemiacetals, they're both viable products. In one of them, the OH group is in the equatorial position. In the other, the OH group is in the axial position. It turns out that the ratio of these is about 67 to 33. That's from your text, and it's not worth memorizing. Something you will learn later in 352, we call this the beta anomer or the beta stereoisomer. Anomer is a new term which I will define later, so don't worry about it now. And the other one is called the alpha anomer. Again, anomer, a term referring to two stereoisomers that differ in configuration at a hemiacetal carbon. 351 review, what is the stereochemical relationship between those two molecules? Are they the same compound, enantiomers or diastereomers, or are they not even isomers? Options A through D, diastereomers, good. You know they're diastereomers how? They're different at one, but not all stereocenters. Good. Yeah, so the relationship between these two, we call them diastereomers. Incidentally, the beta anomer forms in larger amount. You can tell it's more stable, but it's not as much more stable as you would expect based on some stuff you learned in 351, and that is a story for another day. The point you need to realize is that cyclic hemiacetals you can make when you have an alcohol and an aldehyde in the same molecule. One other thing that's worth just saying in about 40 seconds is, your text will have you do this in some problems. If you have a very simple cyclic hemiacetal, you can use an acid catalyst and an alcohol to go from the cyclic hemiacetal to the complete acetal. I don't know, there we go. Sorry, getting ahead of myself. I'm nervous now, somebody's timing me. I told you 40 seconds and I think I'm already beyond that. So you can convert a hemiacetal into an acetal. The way that works is the same way as it works in acetal formation mechanism. You protonate the OH group to turn it into a good leaving group. Then the ring oxygen does the kicking off of the good leaving group to make an oxonium ion like we've done before. And then the alcohol attacks the pi star of the oxonium ion as you've seen before. That's all I'm going to draw for you. I'm going to expect you to be able to draw the next intermediate and the next proton transfer step, and that'll get you to the acetal. All right. So it looks like our time in chapter 14 isn't over as soon as I thought it was. There's one more thing you need to know from this chapter. I've saved it to the end because it's weird. It's kind of out of place relative to the other reactions we've talked about. So far, what we've done is involved acid catalysis on a carbonyl oxygen so that we can have something attack the carbonyl carbon. This reaction fits in this chapter because it's a reaction on ketones and aldehydes. It's included here because it's a reaction that was awarded, its discoverer, Georg Wittig, was awarded the 1979 Nobel Prize for it, and it's still used in organic labs today because it's a reaction that in one step will make two carbon-carbon bonds, a sigma bond and a pi bond. So it's highly useful, but it's totally out of place. It's not related to a lot of the other things we've talked about in this chapter. So that's why I've left it to the end. We're going to talk about the reaction. We're going to draw the mechanism. We'll talk about some of the features. You will need to know how to predict products and provide reagents and use the reaction in a synthesis. So, behold, the Wittig reaction. We organic chemists pronounce the W like the German speakers would. If you want to call it the Wittig reaction, we will smirk at you a little bit, but we will try to be polite. So just whatever you want. Okay, so here's the reaction. I'll show you the reaction, then I need to show you how to prepare the reagent that is used for the reaction. I'm going to be as general as I can to start with. It works on aldehydes and ketones. We're going to start with the aldehyde just to keep things simple. And the reaction involves what is called a Wittig reagent. Thank you for that. That tells me a whole lot about the situation. A Wittig reagent for a Wittig reaction. What does the Wittig reagent look like? Well, you're going to hate this even more. It is something called a phosphonium ylide. Those are two new words. This is, what is this, Duolingo? Can you use it in a sentence? Phosphonium refers to a phosphorus with a positive formal charge on it, a phosphorus bonded to four things. Ylide refers to a molecule where there's a positive and negative formal charge on adjacent carbons. So, behold, the phosphonium ylide. There's the phosphorus. In a lot of examples in your text, the phosphorus is bonded to 3 phenyl groups. There's the positive formal charge on the phosphorus. And then the adjacent carbon, we'll put another R group here. The adjacent carbon is negatively charged. This is the phosphonium ylide. Now, the trick with the phosphonium ylide is that sometimes people don't like to draw plus and negative charges, and they remember that atoms that are from the third row and below on the periodic table can actually accommodate or be surrounded by more than 8 electrons. The octet rule doesn't really hold for atoms that are from the third row and beyond of the periodic table. And so you can draw the structure of the phosphonium ylide as this sort of resonance structure where you move the electrons on that negatively charged oxygen to form a pi bond with the phosphorus. Blasphemy, I know. That's why go ahead and, if you have pearls, you can clutch them in horror. But I like to draw it as this resonance structure just because it's a little bit easier to follow what's going on. It's useful to color code things as you're learning this. We'll color code the carbonyl carbon blue, we'll color the carbonyl oxygen pink, and then let's color the negatively charged carbon orange. In the product, we make a new pi bond, a new sigma bond, and a new pi bond between the blue carbonyl carbon of the aldehyde and the orange carbon of the phosphonium ylide. So I'm going to illustrate that here. Here is the orange carbon, and there is the possibility for stereoisomers. So you would expect to get, in some ratio, both the cis and the trans isomers. Your text may or may not explore that in a lot of detail. There are subsequent developments in organic chemistry that allow you to have some control over the stereochemical outcome as to whether or not you get the E or the Z isomer. I simply want you to be aware of both of them. The other thing you need to know is what happens to the carbonyl oxygen, and that is it ends up bonded to the phosphorus. And this is called triphenylphosphine, and it is very stable. Actually, phosphorus-oxygen bonds are quite stable. You can choose to draw triphenylphosphine oxide. Sorry, I said that wrong. I'm not going to write down the name. You don't need to know it. Triphenylphosphine oxide is very stable, and its formation is a major driving force for the reaction. You can draw it either as I've done on the left or here on the right, but that's where the carbonyl oxygen ends up. Okay, so that's the what. But you can tell how useful this reaction is in a synthesis because it's what we call a convergent reaction. That word means you're taking two parts. I'm going to illustrate those parts with highlighting because, yay, colors. And the green portion, and then I need a new color. The other green portion, let's go purple. Only problem is purple and pink appear same on the screen. Anyway, you're bringing two separate things together, two simpler pieces together, and connecting them to a more complicated molecule. So this is highly useful in organic synthesis. Questions about the reaction so far? Yes?
Just to confirm, the phosphonium ylide is the reagent.
The phosphonium ylide is the Wittig reagent. Yep. Right, what else? Yes?
Could you use something else that like silicone or sulfur that?
Could you use something else from this third row? Phosphorus works well. I don't actually know the answer to that question. It's a good question, and I don't know. From what I've seen, phosphorus is the atom of choice. Others? Okay, so I'll show you mechanism, I'll show you example of synthesis, and then I need to show you how to prepare the Wittig reagent, because you can actually do that using the stuff from the text, and your text in synthesis problems will expect you to do that. So mechanism, really quick, it actually is easy to draw. There's a lot of things going on at once. The easiest thing to do is to draw the phosphorus here and the carbon here of the phosphonium ylide. And then I'll just abbreviate the phenyl groups like that, and there's the positively charged phosphorus. So what you might predict if you know about carbonyl chemistry is the negatively charged oxygen, whoa, I'm going to do that. You might predict that the negatively charged oxygen of the phosphonium ylide would be a nucleophile and attack the carbonyl carbon. So that happens. Attack the pi star and break the pi bond. At the same time, lone pair electrons on the oxygen attack the phosphorus. So that's sort of three things going on at once. If you follow those arrows and look at the consequences, I'm going to continue to highlight in red the new bonds that we made as part of this process. We've made two new sigma bonds. One between the carbonyl carbon and the negatively charged carbon of the phosphonium ylide, and then the other between the carbonyl oxygen and the phosphorus. So if I want to keep our highlighting consistent with what we did above, blue and whatever, orange, that's where the sigma bond comes from. Then what happens next is something that we don't need to spend a ton of time explaining. Electrons, and there's actually two ways to draw it. You just have to pick one. Electrons from the carbon-phosphorus bond are going to kick down to form the new carbon-carbon pi bond. At the same time, the carbon-oxygen sigma bond is going to shift over here to form a new oxygen-phosphorus pi bond. That's going to result in the triphenylphosphine oxide product here, and then the alkene product here. And because I don't want to, I'm not going to draw the Z stereoisomer. Okay. So that's the mechanism. You form a four-membered ring and then it breaks apart. Driving force for this is probably release of ring strain along with formation of the very stable oxygen phosphorus sigma and pi bonds. Yes?
Does phosphorus still have the positive charge with the intermediate?
In the intermediate here, yes, phosphorus still has a positive formal charge. Let's see, what did I miss? 5 bonds. No, you're right. 4 bonds to phosphorus. Thank you. I got a minus 1. Formal charge mistakes are usually -1. So -1 for me. Put that on my tab. End of semester reviews. -1 for formal charge for me. Okay. Yes, the phosphorus there with 5 bonds should be neutral. You can do the math if you see the periodic table. Other questions? Okay, I told you we needed to figure out the phosphonium, how to make the phosphonium ylide. So you start out with, if this is your end goal, if you want this phosphonium ylide, then you're going to start out with, if that's your goal, you're going to start out with the corresponding, and I'll continue to label the negatively charged carbon of the phosphonium ylide there. You're going to start out with the corresponding alkyl halide. So the carbon that is bonded to the phosphorus begins by being bonded to a halide as a leaving group. The first reaction uses triphenylphosphine, phosphorus bonded to 3 phenyl groups, as a nucleophile in an SN2 reaction. Essentially, this is just backside attack, kicking off the leaving group, the halide leaving group, to create this intermediate. Now notice that we're almost to the phosphonium ylide, only the orange carbon is neutral and fully saturated. The bromo leaving group sort of sticks around as the counter ion. This is sometimes called a phosphonium salt. Notice that this SN2 reaction is fast for primary alkyl halides. It's going to be slower for secondary alkyl halides. More on that in a little bit, but that's a review from 351. Then to make the ylide, you gotta remove a proton from the orange carbon. You need a really strong base to do this, and the base of choice is called N-butyl lithium, or alternatively, it's an organolithium reagent like that. That just happens to be fairly inexpensive to get. We're using it not as a nucleophile now, but in its capacity as a very strong base to simply remove the proton and generate the phosphonium ylide. So generating a Wittig reagent, you can do that from the corresponding alkyl halide in 2 steps. First, the SN2 reaction with triphenylphosphine, then remove the proton with N-butyl lithium to make the phosphonium ylide, and that is the Wittig reagent. Now I said something about that SN2 reaction, and this is important. Sometimes the fact that you have to do, and often the fact that you have to do the SN2 reaction to make the Wittig reagent influences your choice of synthesis. So, as an example, suppose your target is this molecule. Okay, fine, methyl groups are boring. Let's make it an ethyl group. Now we're very much more interested. Okay? So when you do retrosynthesis, you break the molecule up conceptually in your head into 2 different starting points, or into 2 simpler starting materials. So I would see this sigma and the pi bond, and I would say I can make that via a Wittig reaction. The only thing is now I have to decide which side do I think was my carbonyl and which side do I think was my Wittig reagent. You might say, okay, one strategy would be to use this as a ketone, and then use, and then the Wittig reagent would be the remaining portion, right? A 3 carbon, and then there's the phosphonium ylide. So that would be one way to do this. Alternatively, you might ask, could I not have the ketone be on, or the aldehyde be on the sort of shorter upper half, and then on the lower half of the molecule, could I not have that be the phosphonium ylide? And it turns out that this method up top is preferred, and this is unpreferred, not preferred, worser. Worser is what we will say. The reason has to do with the reaction you do to get the phosphonium ylide. Here, as I showed you, you could start out with a primary alkyl halide. You could do the SN2 reaction very fast and super efficient, starting with the primary alkyl halide, and then use, as I showed you above, N-butyl lithium to make the Wittig reagent, as opposed to here, you would have to start with a secondary alkyl halide. And as I told you, the SN2 reaction is less efficient there. And so that's why the top method is preferred. That's important. It's actually ridiculously easy for me to ask an exam question about that issue. So I have fully disclosed that here. Just review it and make sure you know how to do it. Now, this puts us maybe one full day behind. Fortunately, I wasn't ever going to spend 2 days on chapter 15 anyway. So next time, come prepared to be done with chapter 15 and we'll move on. Have a great Monday.